Yeah, okay. It's okay. There is a red light, so
Okay.
you are on air.
Wow, let's go. So good morning or good afternoon, everyone. I don't know where you are located. My name is Adrian and I'm with Luis, and today we are going to talk about what we mentioned at the initialization challenge for digital twin with our models. Just to mention, this project is a collaboration between three actors. So basically it's Coris, the main headquarter in Grenoble, with a laboratory, a control laboratory in France, quite a famous one in Grenoble called EgyptSalab. And this is where Louise is also working. And finally, we have an industrial partner, and this is a production site at Framatome, which is one of our shareholders. This production site is responsible for zirconium production, which is used for nuclear power plants. But we will talk about this a bit further in the presentation. We are going to start with an introduction, just to mention what do we call a digital twin. We are going to give a few definitions because it's quite unclear what it is and what we expect it to be. Then we are going to move to the initialization challenge, what it is, how did we manage to tackle this, what are our options, and finally we will see an industrial example. So I mentioned Framatome at the Jarry site. This is our example and the results we have for the solution we imagine. So let's move on the overview and concept definition. Here is a kind of a main definition of what is a digital twin. So a digital twin is a representation of a real assets. So this is the digital representation that is dynamically updated and that helps decision making. So it's quite general, but you need to have both a digital representation and a dynamical update. So you could call it a digital twin. Nevertheless, if you just Google digital twin for a few minutes, you will end up with a lot of results and a lot of articles of many big companies that are going to explain you different concepts of digital twin, that have their own vision of what it is. And we might have a specific one, so I'm gonna explain it to you. And just to mention this, if you do a Google trend of digital twin, you could see that it's kind of a buzzword, where we could have this word searching more and more for the last few years. If we look at the plant's life cycle management, here is how we could decompose some kind of digital twin vision of the process. At the very beginning, you have the basic design on the planning. And if we try to do a decomposition for model and data, we have a very high level model. And the only data we have are plant specification or rules, nothing very precise. But we have data, we have model, we could do dynamic updates. Some people can call this a digital twin. Then we have the detailed engineering. Once we have finished the basic design, here we started to have some PID, control schematic, some controls, ESD, and all that stuff. And we can try to do a more physical model, get a more physical, practical approach to this. So it kind of look like a digital twin. Then we move on to the commissioning, which is a key point because it's the first time that we are doing the startup and we have the data from the real plant. And finally, you get the normal operation. And then you are supposed to have a high fidelity model at that point that have been validated through the commissioning and all that stuff. And you get a continuous flow of measurements that is coming from your plants and that you need to treat. If we try to split this into two separated parts, I would say that on the left side, we would have what I call here the abstract digital twin. So we use it such a representation. You might call it a digital twin. Some call this a digital twin. This is not our vision of it. And then we have here what I've called the connected digital twin, because now we have real data from measurements that are coming to us at any time steps. And this is what we are going to focus on because it's the one we use for decision making. And all the stuff we are going to explain in this presentation is focused on as if we have a model, a high fidelity model, and we are in nominal operation, and we are able to get data from plants at, let's say, every time steps. So this is really where we are going to focus for the digital twin. Okay. So a digital twin is used for multiple industrial applications. So the first application we are aiming is the online fault detection. Basically, we want to be able to prevent a failure in a very short scale time range. So maybe, I don't know, your valve is stuck, and we need to detect this in a very short time scale range. So we could tell this to the operator, and they could act properly on the process to prevent any breaking or any shutdown of the production. Then we have what is called the predictive maintenance, which is also the capacity to detect any problem, but it's on a long scale time range. So the idea is to predict when the equipment is going to fail in the next future, in maybe the next month or the next year, just to see if we are able to prevent it and to schedule some maintenance in order to avoid, once again, either a production shutdown or to break any equipment. We move on to what we call here virtual sensors, or for those of you which are familiar with automatic control, which is called observers, basically in mathematics. And it's the capacity that we have to measure it with the model, unmeasured data on the real side. Most of the time, you do not have analyzer or density analysis everywhere on your process. But if you get a correct model, which is, let's say, in tune with the real process, then you could use it as a virtual sensor to get more information into your process, which helps you for decision making. Another subject that we have seen a lot recently is what is called alarm forecasting. So this is the capacity to predict when an alarm is going to happen in the future. Imagine that you have a big drum and your level is slowly decreasing, but too slowly, so it could be viewed by, let's say, human eye on a short time scale. We are able to say, be careful, maybe in 2 hours, you are going to reach the low level in this drum. And then you could act before you are, let's say, in the panic mode and you do not have enough time to correct the problem. Of course, there is the topic of optimization, which is kind of old one. You could use your model, you could use your digital twin to optimize your process in terms of production, in terms of energy consumption, or whatever you want to optimize. Then you get a what if scenario. So what if scenario, basically, you are in your real plans. You are not sure if the action you want to do is good or not for your plans. What you are going to do is to move to the simulator, do this action, leave the simulator running for many times, and just check if you have done the correct stuff before doing it on the real plans. And you could perform this analysis multiple times at multiple moments. And of course, this is our main business, you know it, this is operator training. If your digital twin is closer to the reality, then the training is better. For all these applications, so this is not only our vision, this is also, if we look at the industrial, what they are looking for, this is what they are looking for when we talk about digital twin. And if we look at this one there, the very basic of it, we need to be able to initialize the digital twin to the current state of the plant. Let me explain it to you. Imagine we have a real plant with measurement. We will call them the past measurements there, and we are at the current time. At some point, we want to be able to say, okay, I want to synchronize my digital twin, my model if you prefer, with the real plant using the past measurements. Once we are able to do this, then we could use the digital twin to predict the future, and with this prediction, to improve our assumption on the system and improve our way to control it. So this, for us, is the main problem of the digital twin. It is to be able to synchronize the digital twin with the real plant. Then let's move on to the concepts behind the initialization. Let's consider at the beginning a digital twin and a real plant that are not initialized together at the very beginning. The first step is to use the historical measurements to do the initialization. Once, let's say, you are correctly initialized and the state of your real plant is the same one than the state of the digital twin, you could perform many actions. First, you could run the digital twin in real time and do some decision making by comparing the value of the digital twin with the value of the real plant. Basically, if you get the value of the real plant that goes on one side and the digital twin on the other one, maybe there is something strange, and we could say to the operator, the behavior is strange. Have a look at these values because it didn't seem to be correct. We could also run the digital twin faster, and we could do prediction. So that's the kind of what if analysis. And of course, we need to close the loop. At some point, we need to say, okay, this is the real plant, this is the digital twin. Let's do some comparison and recalibrate the digital twin online to be sure that both digital and real world are still aligned. So if we look at the big picture there are two main problems. So the one I've already spoken about, which is the initialization challenge. How do we do this? And the second one is how to perform the calibration, the online calibration. For this presentation, we are only going to focus on the initialization challenge. Actually, with Luis, we are also working on the other one, but it is not the topic of today. So let's move on the initialization challenge a little bit more. First, we need to define our scope. Of course, we are working with nonlinear system. You all know about it. We are working with large-scale plants. Even if our example is not that large, I'm going to explain it. We need to have a possibility to initialize the digital twin with the real plants quite fast. We are not willing to have an algorithm that makes hours to get the initialization. Like basically, the operator should come, press the initialize button, and then in let's say a few minutes maximum, it should be okay. And of course, we are dealing with a large number of parameters and variables. It is extremely important to mention that on the industrial world, you would find a lot of digital twin examples, but they are clearly not at the same scale. They are at the scale of, let's say, a small compressor, a small motor, an equipment, but never at the scale of a full plant. And this is the very big challenge and the very big difference. So you could see a lot of articles, a lot of papers about it, but kind of never about very big scale system. And this is the kind of challenge we are going to tackle there. So this is what is explained there. You should be aware about this. Our main example here is going to be from the Jarry production line for the Iconium. So basically, it is a distillation process. In our case, we consider this process, like in Chorus, we consider this process as small. We have around 1,000 states and 200 equipments, but this is already very big comparing to what you could see on the literature. And this is only the first step, because then we are going to talk about a full refinery or a full nuclear power plant. And then we are going to talk about way more states and equipments. And this is a very big challenge. You are going to see how we try to tackle this. Let's move on the initialization challenge.
So I will consider now. As Adrien said, our main objective here is to find a way to initialize the digital twin based on measurements that come from the plant that give us the real state of the plant. So there are three basic steps, let's say main steps that our methodology is based. The first one is that we get measurements from the plants that we are interested on. So measurements from transmitters, commands that were applied on the plant, if a valve was open or closed, things like that. We of course need to treat these measurements, this information that comes from the real plant, because it might be full of white noise or missing data, etc. And the last and more important step is to find a way to initialize the simulation of digital twin in a way that the behavior of the digital twin is the same or very close to the real plan. And the third step, of course, is our biggest challenge and focus here. So to actually synchronize the digital twin to the plant, we are going to a very specific approach that the softwares available in Coris enable to do, which is snapshot selection. So what we want to do is to use the measurements, as you can see, that come from the plant. So a past, let's say, period of measurements, different measurements from the plant. We want to, assuming we have, of course, a set of snapshots that are linked to the digital twin that we that models the plant. We want to find the best snapshot to actually initialize our digital twin, so that it will be synchronized to the plant behavior. And here we have actually two challenges. The first one is, how do we create this base of snapshots, this database of snapshots? How are we going to populate this, let's say, library of snapshots such that we explore all the behaviors that is planned and it can be used at. And the second challenge is, how do we select the best, and how do we choose, how do we assume which we got to the best snapshot to initialize the plant, the digital twin, sorry. So we are, in this presentation, we are first going to talk about the first challenge, which is how to create the database of snapshot. So the first thing that it was previously said also for Adrian, is once we have the digital twin that was developed for one specific plant, we have to calibrate it such that the behavior of the digital twin will be at least close to the behavior of the real plant on a steady state analysis. So at least the average behavior needs to be similar. So we have a start point to start varying or digital twin or go into the next step. This calibration we'll talk about later, but it's most likely a manual calibration, okay, where we change some values, some parameters on the digital twin and see how it impacts and if it decrease the error between the real plant measurements and the digital twin. Once it's calibrated, we can actually use the commands that were applied on the real plant on the digital twin, the historic commands that were applied on the real plant on the digital twin. We run the model, and while we are running the model, we can extract the measurements from the digital twin and compare it to the historical measurements from the real plant. And while also the digital twin is running, we can save the snapshots linked to its, let's say, instant on the digital twin. And we can go to the comparison from the digital twin to the historic measurement of the plant to see if our behavior from the digital twin is close to the one of the behavior expected to the plant. If our error between both of these measurements is acceptable, then we would just save the snapshots on our database and assume everything works well. Otherwise, we have to go back to the calibration phase to try to get the digital twin to have a more similar behavior to the plant. Just to say, this calibration now, it's a mix of automated and manual actions that, well, we are trying to make that as automatic possible, but it's not an easy task. But it's not a focus on this presentation either. To improve this snapshot database, which is the main, let's say, the most important database of our approach, it's important to have a good definition of the inputs and the associated ranges that are linked to the behavior of the real plant. Let's say we have a list of set points, manual operator, boundary conditions that will vary on the real plant. And it's important to have these inputs well defined, and also to have the knowledge of what is the range of variation of these inputs. Once we have this range of variation, we can choose multiple points, multiple values, let's say, for each of these inputs. So we can populate the space of interest of variation for the plant, and then we can use this different set of inputs to simulate the digital twin. And in between each simulation, we can save all snapshots linked, of course, to a certain state of the digital twin, of the behavior of the plant. And all of these snapshots, they are being saved, are then saved on a file or a snapshot database that will be used for the next steps of this presentation and the methodology. Again, talking again about this because it's very important to have the process knowledge from the plant that the specific plant of the application. Each let's say each process will have its own inputs, and these values need to be known so that we have a good definition to populate our database of snapshots, and this way the methodology that we propose will work better. Okay, now that the first challenge is let's say done, we populate the database of snapshot. We can go to the second challenge, which is how to select the best snapshot inside of this database of different snapshots from digital twin. So our approach, our proposition of approach is based on the idea that we have a set history measurements from the plant, a set of measurements that will give us what is the behavior of the real plant. And then we will compare these measurements to the measurements that are linked to each snapshot in our database that was previously created. And from this comparison, we will, let's say, minimize the error between the measurements of the plant and the measurements of the digital twin. And our method or approach will give back the best snapshot to initialize a digital twin so that it's synchronized to the real plant. To make it more visual, let's say we have this measurement from the plant, and here the red curve, it's just one measurement, but one measurement, the curve of the measurement in time that we received from the plant. Then we have in our database of snapshots linked measurements to each snapshot. And here the blue curves represent the measurements that are linked to each snapshot. Okay. So what we do is we compare the red curves, so the measurements from the plant, with the ones for each snapshot, and we compute what we call the cross-correlation factor for each of the snapshots. And the red curve is the measurement that comes from the plant. The blue curve is the measurement that is linked to a list of snapshots and different measurements, let's say. The last bottom top is the cross-correlation factor that is being computed. And what we want is to find the maximal factor for the cross-correlation. And this maximal factor will give us the best matching, let's say, all the best snapshots, a set of best snapshots that better correspond to the behavior of the red curve, so the behavior of the real plant. Once we computed these factors for each of the snapshots, we will have a list of factors for each snapshot. And then we can choose, in this case, it's clear that it's the bottom snapshot and the bottom curve that fits better the plant measurements. And then our method, we just return to the user this best snapshot to initialize the digital twin. Now, let's say for overview, we have tackled the problem of initializing digital twin, or we prefer the methodology. But also, not always the snapshot that our methodology we propose will be close enough, let's say, of the behavior of the plant. It actually depends on the snapshots that are on the database of snapshot. If the database is, let's say, very large and well distributed, maybe we'll find a good snapshot, but sometimes that won't be the case. And when we find a snapshot that is not good, let's say, it's a high error compared to the real plant, it might be necessary to actually go back to the calibration of the digital twin. And in this case, we are working on some automated parameter identification or an automated methodology to actually vary some parameters on the digital twin and try to get it to be more close to the behavior of the real plant. But this also won't be this specific methodology, automated methodology. We are not going to be focusing on this presentation. Just an overview of our proposed methodology here. We have 4 steps. Basically, the first one is the data analysis and processing of the data that the plant that will be given from the real plant we are interested on. The second step is the digital twin calibration. The third is the snapshot database creation, and the fourth step is actually the selection of a snapshot to initialize the digital twin. I'm just giving this overview here because next slide we will be talking about an industrial application, and we are going to go through these 4 steps. And this, we will recount each step because it's a big subject. Each of these in real application is one subject itself, and we are going to go through the 4 of them now. So, for our industrial example, as previously said, we are looking at this industrial process from Framatome that the process goals is the purification of the zirconium. Sorry. Here on the side, it's given a scheme, or let's say a representation scheme of the process itself. The process, it's not that big, but still there are multiple different chemical compounds. There is a powder being giving to feed this process. There are also liquid that are over the tubes and etc. So there are lots of different parameters and variables to control here. For this specific validation and example, we are going to look specifically to the subsystem system, which is composed by the bottom of the distillation column of this process, the boiler on the bottom also, and other different machinery that is included on this group here. And for this specific subsystem, we have a set of 25 signals that were given from Framatome, so we could compare to our model, our digital twin. So now we'll be talking about the data analysis and processing of the data to check the sample time, missing points on the set of measurements that are given to us, and to take out some outliers from the data. So this is the set of measurements that we have. As you can see, it's composed of different variables. There is temperature, pressure, weight. When, as I said, there is some powder being given to feed the system. There is the level of some drums, and the behavior of each of these variables are different, as you can see clearly on this plot. Also, not only the behavior, but also the sampling time for each of these variables, it's not exactly the same. Okay, so this is something that for our methodology, mathematically, we have to have the same sampling time and no missing points for the data we are feeding the methodology. Also, in this case, as we previously said, we are going to use the set point and commands. So in this case, there are two set points that are given from the real system, and we are going to use it later to create our snapshot database. Okay, once we have this set of data, we can homogenize it by some well-known data treatment approaches. The first step, we have three steps mainly. It's a, let's say, a presetted methodology to actually make our data homogenic. So the first step is to impose the same sampling data on our matrix of data given from plants. And for that, we are just going to place some empty, let's say, boxes in the vector for each measurement that corresponds to each time step and sampling step for our measurements, each of them. So in this case, 25, 23, etc. Once we have imposed the same data step, timing step, sorry, for all of the measurements, we can do an interpolation on the matrix. So we are going to populate the missing values with interpolated values, in this case using a linear interpolation method from Python. And the third step is to do a principal component analysis to understand the relation between each of the measurements, to see if there are measurements that are, let's say, duplicated, or if there are measurements that are very important or less important, and also to filter our measurements so we can take out the outliers, the white noise, even in the measurements they're taken from the plant. Once we have an homogeneous set of data, we can go to the calibration of a digital twin, where we are going to fit the existing model on the measurements that we just treated to be homogeneous. So here we are specifically talking about Indus Plus model, digital twin. The digital twin is as shown here in this scheme. It's exactly like this. And just to clarify, we have the drum, which represents the bottom of our column, and the boiler to represent the boiler from the industry, and of course some other necessary machinery and to close the loop in this case. So to calibrate this model, we have to keep in mind there are some key values that we are going to be able to change. For instance, the unknown parameters, such as the exchange coefficients, friction factor losses. These unknown parameters are not necessarily unknown, but we don't have as 100% certainty of their values. So we can change them to try to make the behavior of the digital twin be closer to the plant. And also there is the measurement uncertainty. As I said before, there is noise that is included on the measurements that come from the plant. And then we have to keep in mind that we cannot base our calibration 100% on the behavior of the measurements, because most likely we'll have some error on the measurements that is caused by the measurement gadget. And also the uncertainty in this zirconium purification process, the uncertainty of the inlet boundary, for instance, the composition of the feed components that are given to the process is not necessarily measurement all instance. Actually, it's very few times measurements, so we cannot have a certainty about that. So we can also profit of that to change the value in the digital twin and calibrate it. The model, digital twin, the first model we see, it's based on engineering data, right? So even though this engineering data comes from knowledge of the plant, many times it can be obsolete. That being said, the plant can be used for 1 year, 5 years, I don't know, long time. That the values, the characteristics, parameters from the plant might change. And because of that, we most likely we need to calibrate our digital twin and change some of the values that were decided based on engineering data. And this calibration, it's a mix of manual and actions and automated algorithms. First, again, we are going to run the digital twin in its first stage, so based on engineering data, and we compare its measurement values to the real plant values. Then we compute the error between both of these measurements. And if the error is high, we are going to look for the high error values specifically. And we are going to search where these parameters and variables are on the digital twin itself. And once we know what are the variables that are with high error, we can see what are the parameters around this region that are linked to this variable, and then we are going to manually change its value such that the digital twin will have a behavior that will be closer to the real plant behavior. So this first calibration is completely, for now at least, it's manually done. Okay, we do it, we open in Displus, and then we change the values, we extract the measurements, and then we compare. Ideally, what we are working on is to also do this kind of calibration automatically, but it's another challenging. Okay, now let's say we have the digital twin calibrated. We can create our snapshot database using the set points and boundary conditions that were given from the plant and from the real industry. For that, here it's the first example. We are going to use the stat points. So this first measurement, temperature stat point given from the plant, and 3 boundary conditions that were given also from the plant. And we are going to impose these values on the digital twin as input to force the behavior of the digital twin to the same behavior of the real system. So just to clarify, the imposed boundary conditions are on the bottom of the distillation column and on the output of our system, because we, of course, if we have the whole industrial process model in a digital twin, we would not need to impose these values. But since we are looking to a subsystem, in this case, we had to impose these variables. Okay, so once we define the inputs for digital twin, we run in Displus and we save the measurements. In this case, I'm just showing some measurements here, but we save the measurements. It's the blue curve, the behavior of the measurements from the model, the digital twin, and we compare with the real measurements. Okay. Here we can see that you have a similar behavior. It's not 100%, I mean, it's not a 0% error in between both curves. But again, we have measurements that are not 100% trustable. And also, the important for us is that the dynamic behavior is similar. And in this case, it's enough. So while running the simulation, we can save snapshots all along the digital twin is running, so we can populate our database, snapshot database, and then we can go to the next step, which is apply the methodology to choose, let's say, the first snapshot the initialization snapshot, sorry. There are some important information about these processes that we are looking on. The first one is that we are looking to a low dynamic process. In the last plot I just showed, there was 1 week of measurement from the specific framatome zirconium production. So 1 week, we saw all of that variation, but it means that in a 1 hour of measurements, there is not a lot of variation between each measurement. So in this case, we choose to save 1 snapshot per hour. So each hour simulation, we saved 1 snapshot. And that gave us, in the end, about 150 snapshots to populate our snapshots database. Okay. And this choice will depend on the system of interest, of course, and most importantly on how the system behaves, how its dynamic response behaves during the time. So now we can go to the next step, which is choose the snapshot to synchronize the digital twin to the real plan. And for that, here I'm going to show 2 validation cases. The first one, the first and the second one, well, it's just a question of choosing a set of measurements in time from the coming from the real plant. In this case, we have 1 hour of measurement coming from the real plant. So our span time for the measurement is 1 hour, and we have 1 measurement per minute to compare with the measurements from the digital twin. This window of measurement is very important because it will impact let's say, how our methodology will, let's say, work on the process of interest. If we have a small window of measurement, most likely the methodology will have a high error, and you can increase the window of measurements, but at one time it's going to saturate, let's say. And even if you increase this span window of measurements, you won't see any difference. And since in this case we impose the input and set points of our real plant on the digital twin, we know what is the expected snapshot that we should find to initialize our system. It's just a question of validation. It's important to say here that we are using a known set of measurements that were also used to create our snapshot database. So to validate our methodology, we know what snapshot we hope to find as output of our initialization methodology. So here I'm plotting 1 measurement for each of the validation cases, and the yellow star, it's just, let's say, the position of the snapshot that we should get as output for each of our validation cases. For the first case, we applied the methodology, and our result was perfect. We found to initialize Indus Plus exactly the same snapshot that we were expecting to find on a validation case. So we were expecting snapshots around 1 day and 3 hours of the process, the plant data, set of data we received, and we found exactly the same. For the second case of validation, we didn't find exactly the same snapshots, but we found something very close to the one that we were expecting. So we were expecting a snapshot based on about 2 days and 22 hours of data, and we found something around 2 days and 18 hours of simulation. So it's a 4-hour difference, and since our process here has a slow dynamic, this is not a long, let's say, a long time difference between the snapshot. To clarify it and visualize it in a better way, I'm comparing here the plots for different measurements linked to each of the validation case. And the blue curve is the expected behavior from in the plants that we were expecting. And the red curve is the behavior that the snapshots that was found to initialize the system gives. On the first case of validation, the snapshot is exactly the same. So the curves are superposed and have no error. And the second case of validation, we have a small difference. All the curves are normalized. Sorry, I forgot to say that. But we have a very small difference between the behavior that was expected and the behavior that was predicted. To be, let's say, more precise, there is an error of about 5% between the red curve and the blue curve when for the variable where we have more errors. So this one, which I'm pointing here. Okay, and also it's not very, actually, it's not very visible here because all the variables are normalized, but the variation window for each of the variables of this process is not very big. So even though we have a small variation for each measurement of the plant, we were able to actually find a snapshot that allow us to simulate our digital twin in a behavior very close to our process of interest. So it's a very good result. So to conclude, we have seen that the minimal distance approach, it works quite well for the application of the subsystem of this real industrial scenario. And we saw also there are some sensibility. The most important is how we choose this window for the measurements that we come from the plants for the comparison. There are some advantages of using this approach. The first one is that more we populate our snapshot database, we have a better precision in our results, and we don't need to train any methodology. We just need to populate our snapshot database, and we're going to do the research of the snapshot inside of the database. Some disadvantages is that also when we have a very well-populated snapshot database, we will need more computational time to compare the measurements come from the plant with all of the measurements inside the database. And there were some instabilities when we have a lot of transition or, say, peak values on the measurements coming from the plant. Other methodologies were also developed and tested while we were developing this work to treat a process that we need a very big snapshot database. For instance, we did a classification methodology that seems to work quite well, but we did not. I'm not going to enter in detail here. And our next step for this work is to apply the methodologies presented here on a full scope plant, the same process from Jarry and the zirconium plant, which brings much more measurements and variables to account for, and also a more complex, of course, system. And our second work in progress, as Adrien already said, is that we are developing a parameter identification to be able to automatically calibrate our digital twin depending on its behavior in comparison to the real plants. So thank you for your time. I will be happy to answer any question.
Thanks a lot, Louise and Adrien. If there are questions, I propose to to add them to the chat. It will be easier for us to identify the person. No question. Everything is clear.
A commercial presentation. So the question is, okay, great job. Is there a commercial demonstration that is being prepared for this? That is a question that we were asked many times. We are working on that topic. The only problem we have there is the intellectual property, because the system we showed you, this is why data were all normalized. It's because we are not supposed to show the real value from the real plant. This is completely intellectual property from Framatome. So yes, we are working on it. I think you could get close to Didier to, let's say, define a schedule if you really need one, but we will be happy to help and do this. What is the timeline for this? So actually, we do not have the timeline for the demonstration. Would you say that we are supposed to finish this work, that the next step you've seen there on the last slide, until the end of the year? That's about the idea. Next question. At the beginning, I had a confusion because it seems you spoke about a snapshot with an history, not a single point. You want to answer, or should I?
So yeah, that's actually a very good question, because in our let's say definition, we actually use the snapshot definition to talk about, that would better, to talk about the snapshot file that is linked to the simulation. And we implemented a program in IndusBlue that allow us to actually extract the measurements from IndusBlue and let's say at each instant of measurement, we couple the name of the snapshot file where these states are going to be saved. So actually, our snapshot definition, as shown in this slide here, is exactly like that. It's the snapshot file and a set of measurements for a period of time. And it's actually a very let's say smart way to couple the snapshot file and use it without being actually needing to get inside of it or open it, because of course it's a binary file and will cost a lot of time and work to actually find all and understand all of the information there.
So yeah, so there is snapshot. Usually we call a snapshot just a file at a given moment to the photos of the simulator, but here you clearly have the snapshot file and the historian, like they say, the last hour before the snapshot on the simulator, they are all saved on the same variable. And also, why do we do this? It's because if you just look at one moment in time, you could have a process that goes straight to the top. And if you take the exact same process that goes straight to the bottom, let's say an increasing level or a decreasing level, at some point they are going to have the exact same value. But if you do not capture the dynamic of the process, you are not able to identify, I am increasing or decreasing the value. So this is also very important for us to have historian for, let's say, 1 hour here, just to be able to discriminate the cases when we need to synchronize our digital twin. So Philippe also mentioned that, yes, the example that we used there with Framatome Jarry, that the people that we are working with, they are going to be there at the Simtech in France. And just to mention that it is a very nice opportunity that we get, because we, as Chorus, have the opportunity to work with a pretty nice laboratory in automatic control. And at the same time, we have an industrial partner that is willing to share data and knowledge with us. And we have discussed with other partners or other people also working on the same subject as we are. They do not have any industrial data. A lot of people are just working on, let's say, academic example or very small process or only simulation. And they are not being confronted to, let's say, the reality and to real measurement and to the noise, to the missing data, to the outliers, all that stuff. And I think it is pretty good for us because it gives us some legitimacy. So the results we are showing there, they works on real data from a real plant. So it means something rather than just to say, hey, I get a double inverted pendulum, like what a classical academic example, and it works. It's not an industrial application in that case.
And I think the last comment is about the commercial stuff to convince our customer. And I agree that today the aim of this conversation and this demo is to share a technical point of view with the technicians. And obviously, we will have to have a commercial package, a simplified commercial package for this.
Speaking of commercial overview, we already talked about it with Jean-Christophe as well. What you need to understand there is that it is extremely complicated what we're trying to do. For what we could see with Louise on all the analysis we've done on the paper and the journals, nobody is able to do this at a full-scale plant, basically a full refinery or a full nuclear power plant. Like, we didn't see any example of it. Nobody advertised it. So one thing what might be difficult, we might have some challengers that say, hey, we get something that works. But I think they play with the definition of digital twin, and this is not what we presented there with the possibility to synchronize your model with the real plants. And this is something kind of difficult with our clients. We need to persuade them to convince them that maybe someone else told them something which is not true or not the overall scale process.
Okay, other question? So if there is no other question, I propose that we close this conference. So again, thanks to you for the work, Louise and Adrien. And we'll share the video for those who want to review or to share with other colleagues. So wish you all a nice end of day, and see you, all of you, soon.
Thank you very much for your time. Have a nice day, evening, morning, whatever.
Thank you very much.
Yes, we will share the presentation that will be online for everybody. Have a great day. Bye-bye.
Yeah, bye.